Welcome back. We got some more relation topics here. Inverse, composition, software, matrix multiplication, modular and clock arithmetic, and N-ary relations. So this is just to round out our discussion of relations and help us get set up for the implementation in software that we're going to do. And then modular arithmetic has a relationship to encryption, and N-ary relations leads us into relational database, which is the next topic. Okay, so let's kind of go through this stuff here. So we have something called the inverse of a relation, and basically we can just swap all the pairs and get the inverse. So that's about it. And so the inverse is defined that if you have a pair AB in some relation, then the pair BA will be in the inverse relation, and we use r to the minus 1 for the notation for inverse. So here's an example. Let's take a set A consisting of these three elements, little a, little b, little c, and a set capital B consisting of x, y, and z. Then you could build a Cartesian product, which would be a bunch of pairs, and then we can pull out some arbitrary elements from that Cartesian product and call it R, a relation, right? A relation is just a subset of the Cartesian product. So anyway, we got this arbitrary collection here, or set of pairs, AY, BX, BZ, CZ. So that would look like this in the digraph. R would look like this. You put the domain here, A, B, and C, and then you put the range X, Y, and Z here, and then you draw the arrows. It looks like this. So the inverse would just be flipping all of these pairs. So you're basically flipping the arrows. So like you have an arrow coming from A to Y, just put the arrowhead on the other side. So there it is. Now it's coming from Y to A. Well, that's about it. And you just flip all these arrows. Sometimes you'll move the sets. That is, you put B on the left and A on the right. So that's the inverse. It's really pretty simple. The last thing we could point out really is that, if the original relation is a subset of A cross B, then the inverse is a subset of B cross A. We could say that the inverse, well, we could say this. We could say that the original relation R maps A into B. We say that sometimes. Maps A into B, and then the inverse relation in this case maps B into A, or B into A. We say stuff like that. Oh, hey, that's what I got in the notes here. That's where I get this stuff. It's all written down. Okay, we can do the composition of two relations. So if we have one relation that maps one set into a second set, and then we have another relation that maps the second set into a third set, then we can say that we'll have a composition that maps the first set into the third set. That's what this is saying a little bit more mathishly. So we have relation R1 that maps a set A into a set B, and then, well, this should be a 2 here. This should be a 2, typo. I'll have to fix that in the notes. And then we have a relation R2 that maps B into C. Then the composition R3 would be denoted like this. So we'd say R1 composition R2, and we use this little circle. And R3, the composition R3 would map the set A into the set C. So basically, if there's AB in R and BC in R2, yeah, AB in R1, BC in R2, then AC will be in R3. And it looks like this. If you drew a picture, kind of at an abstract level with just using these letters and stuff, it would kind of look like this. It's better if we use numbers, but anyway, abstractly, it looks like this. So we've got R1 that maps A into B, and we've got R2 that maps B into C. The composition R3 down here would map A into C. And this little arrow here would represent an element of R1, right? This would be an ordered pair. This arrow here is an ordered pair that's in R1. And this arrow comes from an ordered pair that's in R2. And this arrow right here comes from an ordered pair that's in R3. With numbers, once again, with numbers, here you go. So I've got 1, 3, 5, 7. I could make a relation on this original set. So once again, you take this set, you generate the Cartesian product, you pull items out, and you get a relation. So I've got an arbitrary relation right here, just arbitrary, that maps A back into here. So it maps A back into A. So R1 is 1, 3, 3, 5, 5, 7, 7, 1. It looks like this: 1, 3, 3, 5, 7, 1. That's R1. And then I got another arbitrary relation, R2, which is get my dual pointer action going here. So I've got 1, 3, 3, 3, 5, 3, 3, 1. So the composition, well, we've got several things we could do. We could look at the inverse of R1 and the inverse of R2. We could look at the composition R1, R2, and we could look at the inverse of the composition R1, 2. Just some stuff we could do. So the inverse of R1, you just flip the pairs. So flip this pair, flip that pair, right? Flip the 5 and the 7 to 7, flip the 7 and the 1. That would be the inverse. You could do the same thing with R2. You flip, 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 flip. Okay, then the composition, you got to kind of walk through from one relation to to the other, from one, I guess these are sets. You got to walk all the way through. So start here, 1, 3. Then you look for something that starts with a 3. Here it is. So you'd go 1 through the 3 in the middle, then out to a 3. So you'd need 1, 3 in there. And so there it is. And there's also another one that starts with 3. So there'd be 1, 3. So then that'd bring you to this 3, which brings you to a 1. So we've got 1 through the 3 to 1. So 1, 1. So we need 1, 1 in there. Likewise, there's a 3 to 5, and then a 5 to 3. So we're going 3, 5, 5, 3, or 3 to 3. And, 7 to 1. And then 1 to 3. So there should be a 7 to 3. 7 through the 1 to 3. And that's what's represented here. I got a 1 to 3, then a 3 to 1. So I got 1, 1. 1 to 3, 3 to 3. I got a 1, 3. Like that. What else can we say? We lose this 7 doesn't show up as a second element in this composition. Right? There's no 7 at the end. It's just lost because right here, we sort of, nobody goes to 7 in the first one. Now that's not important what I just said. I mean, there's other things that are just as notable about that. But anyway, this is the composition. You could flip all the pairs in this composition and get the inverse composition. You're just flipping the pairs. Okay, so that's the idea of a composition. Let's see. Yeah, there's other weirdness that happens, none of which is particularly important. There's just weird things that happen when you do the composition. Okay, so it's a real pain to figure out the composition. It's going from 1 to 3 to 3 to 3, gives you 1 to 3. That, if you wrote code that was just looking at these items, it would be a mess. It would be kind of messy. It's not a particularly good way to determine the composition. So we have a more algorithmic, cleaner algorithm, basically, which uses matrix multiplication to determine the composition. And we'll look at that in a little bit. Okay, so I do want to point out, in our notation, we use this circle for composition. And it means start with R1 and then do R2. Now, if you're looking in other books, in other disciplines, sometimes they flip the order of operations. Okay, so just be aware that if you're Googling stuff, Google, and you might be pulling up something that has it all reversed, which is fine. It's just that different subdisciplines, academic subdisciplines, do things a little differently sometimes, so be aware of that. All right, we're going to write programs. So how do we stick a relation in code? How do we represent a relation in software? Why would we do that? Well, most of the time we're doing lookups. You remember, was it rock, paper, scissors from the previous lecture. Go look at that if you need to. Or Animal Farm I had in there. So sometimes the only way to define relations between elements so that you can do a comparison in code, right? In code we write comparisons, right? If this and that, then do this other thing, right? We're writing a comparison. The only way to do comparisons sometimes is by a lookup table, because like rock, paper, scissors, you would just have to look that up. There's no mathematical relationship. There's no mathematical calculation that you could do to determine if those two things are related. So that's the most common thing we want. And in code, that might look a couple different ways. You might call a function, right, that would look like this. It would return a Boolean. It could be an int. Depends on the language. It would return true, false, basically, which sometimes is an integer. But there's the function call, and there's the arguments you're passing in there. Or some languages would support an expression notation. You could say, if if x are less than y, I guess, if you had less than defined, that would be expression notation. Or this would be, up here, this Boolean would be if r x, y, you call a function inside of an if or something like that. Or you could do a table lookup. You could say if r, now I'm using C syntax. I'm also using C++ syntax at the same time. Amazing. Sorry, a little bit of sarcasm. I shouldn't do that, but yeah, C and C++ they're very similar. Okay, beneath the syntactic notations given above, yeah. So you can do. This is just what it would look like in syntax if you're doing a comparison with different notations on a relation, right? So there's different ways to represent relations in the code algorithmically. But underneath that, what would be inside this function if you called this function? Well, it could be a table. For rock, paper, and scissors, could be a table. What about less than? For less than, well, that you could do with an algorithm. You could look for the biggest one on the left, right? The first guy that has a 1 on the left, he's bigger if it was an integer, your comparison. So some things can be defined algorithmically, and some things have to be defined discretely. That is inside, underneath the syntax you use to access that functionality. All right, I hope this is making sense. Make you think like a coder a little more betterer, I guess. Okay, here's an example. Let's say we have a set, big A has these little letters in it, and then big B has these numbers in it. We generate A cross B, and we pull guys out, and we get R. So R is this set of ordered pairs. It's just a arbitrary set of ordered pairs that I've pulled out of the Cartesian product, A cross B. And A2, A3, B4, blah, blah, blah. So you could just stick them in a table. You could put the first elements on the rows and the second elements on the columns. And, so this is A2 right here. This is A3, this is B4. Okay, so this is the simplest way to represent a relation in code. It's a two-dimensional table. Yeah, that's that. Here's another example of, well, the first example, we're crossing capital A with capital B, two different sets. So reflexive symmetric transitive doesn't apply. Just want to point that out. RS and T, reflexive symmetric transitive, only applies when you're crossing a set with itself. So let's do that. If we crossed a set A with itself and then pulled out a relation, which is a subset of that crossing operation, let's say this was what we pulled out. This is the elements that we pulled out of the Cartesian product, and we're calling this R. It's a relation. So what does it look like? So this guy is, I think this is RST, right? Yeah. No, it's not transitive. Okay, it's not transitive. So, but it is reflexive, because look, I got 1, 2, 3, 4, 5 in the original set. So to be reflexive, I need to have a 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, which I have. Which, by the way, is the diagonals. So if it's reflexive, then all the diagonals will be marked. 1 just means you're in the set. Okay, the 1 indicates membership in the relation. Then I got a couple of symmetric things. So 1, 2, 2, 1, that's symmetric. 1, 3, 3, 1, that's symmetric. 1, 5, 5, 1, that's symmetric. 2, 5, 5, 2, that's symmetric. So this thing should be symmetric. And you can tell by looking at the mirror on either side of the diagonal, right? If you just look on either side of the diagonal, I got 1, 2, 2, 1. It's mirror. This guy, that guy, that guy, that guy, that guy, that guy is mirrored. So it's symmetric. What about transitive? It fails transitivity. This guy is not transitivity because this red square, but my printer is breaking. It won't print in red because it's broken. It fails transitivity on at least this count. There might be another one, but 5, 1, and 1 or 3 are there. Therefore, to be transitive, it would have to have 5, 3, and it doesn't have a 5, 3. Right? It's got a 5, 1, and a 1, 3, but no 5, 3. There's no 5, 3 in here, so it's not transitive. I'm stating that it fails in other ways, but I'm leaving that up to you to find them. So anyway, this guy is reflexive, symmetric, but it's not transitive. Therefore, it's not an equivalence relation. Okay? So we want to write a program to do this. So what would that look like? Okay, so what would finding reflexivity, symmetry, and transitivity look like in code? Well, you know, there's the reflexivity check. You just loop through A and check every element AA, where A is an integer, or the index. You just loop from 1 to 5 and check that. And if any one of these is not present, it's not reflexive. That's it. That's what the algorithm looks like. It's a single loop. What would symmetry look like? What would symmetry look like on this dude? Well, you have to do a nested loop. You have to loop through, you could call this rows and columns, I guess. So you could loop through the rows from 1 to 5 on the outer loop. And then for each row, you'd look at the column, and then you just check. Well, I guess, you know, with this thing here, I'm flipping A and B and B and A, so it's not really strictly correct to say that I'm looking through rows and columns because I'm flipping them around in here. But basically, you try every combination of A, B, and that's the nested loop. This is just trying every, you know, every AB pair, every AB pair, basically, and then you're checking that against a BA pair, you know. That's what the inside's doing here. So if remember, symmetry looks for if there's something in there, then the other thing has to be in there. So if this guy is true, and then this other guy must also be true. That's what this code is saying. And if that fails, then it's not symmetric. So if there's one of these guys here, if there's an AB but there's no corresponding BA, it's not symmetric. And then you could just bail at that point. You could break out of the loop. There's no reason to check the rest, right? You could optimize this by breaking out of the loop. What does transitivity involve? Well, so I'm saying this guy over here is not transitive because it's missing this square right here. It's not transitive. That's pretty hard. It's not obvious how to check that. So we have an algorithm, okay? And we'll look at that in a minute. We'll come back to that. Okay, one more summary example before we look at the algorithm that we're going to use to check for transitivity. So we've got one more summary example here. So remember less than, remember that guy? We have, or actually less than or equal, remember him? We talked about him a lot. So this is less than or equal, right? 1, 1, 2, 2, 3, 3, 1, 2, 1, 3, 2, 3. All of these pairs are less than or equal, you know, to each other. Looks like this. It's reflexive. The 1, 1's in there, 2, 2's in there, 3, 3's in there. That's the equal part. And then the 1 less than 2 is here, and the 1 less than 3 is here. The 2 less than 3 is here. So it's anti-symmetric, right? Because for every AB, there are no BAs, excluding AA, right? This is antisymmetric, and it's reflexive, and it's transitive. Oh, yeah, so it's a, it's reflexive, it's not symmetric, it's also antisymmetric. Remember, these antisymmetric and not symmetric are not exactly the same thing, but they're similar. But anyway, this guy happens to be not symmetric because you know, this one breaks it. It has a 1, 2, but no 2, 1. That breaks this symmetry, so it's not symmetric. It also, but it happens to be antisymmetric because for every AB there is no BA, so that's antisymmetric. In this case, for this particular data, these look very, very similar. You'd have to think, go back and look at the notes for some examples of other variations on this, but this particular set of data, it's hard to see how these are different, but they are slightly different. Anyway, it's not an equivalence relation. It's not an ER because it's not R, S, and T. It is a partial order relation because it's reflexive, antisymmetric, and transitive. And it happens to be a TOR because all elements are comparable. Any two elements pulled out of here will show up either as AB or BA. That's comparable. All elements are comparable. Okay, so that's just one final example. All right, look, to do transitivity, we need a better algorithm. Let's look at that. And our algorithm is matrix multiplication. Okay, so some of you may have seen this in one of your math classes along the way. Hopefully you have. But if you haven't, don't panic. It's a little tricky, but not too hard. Okay, a matrix is just a 2D table, and we can perform a special kind of a multiplication on those tables called matrix multiplication. So this is useful for two purposes for us. For us, we have calculate the composition of two relations, and we can also determine if a relation is transitive. So I'm going to go through matrix multiplication here. So look, here's the deal, matrix multiplication. So if we have a matrix A and a matrix B, now in this case A and B are different matrices. It'll work on different matrices, and you need that for composition, right? So for composition, A and B need to be different, but for transitivity, we're just going to use A, so it'll be A and A. Anyway, but this is the general case where A and B are different. Okay, for just one table, A times A, it'll be easier than this. Anyway, so A is an M by N matrix, so it's M rows, N columns, and B is a N by P matrix, or N rows and P columns. So you have to have the same number of columns in the first one as you do rows in the second one. So N, little n, this guy is as wide as this guy is high. Then you can calculate the resulting matrix C, this guy, and it will have dimensions M by P. So it'll be as tall as this guy, M, and as wide as this guy, P. And the way this thing works is you're looking at each row in this guy, and then you're looking at each column in this guy, and you're walking down the rows. Or let me say this, you're walking across the column here at the same time as you're going down the row. So you're going kind of like this. And so you're going to take two numbers here and multiply them, and then move down and find two more numbers and multiply them, and two more numbers and multiply them, like that. You're going to walk down multiplying and then add all that junk together, and that sum goes in here. That's what this says. If you prefer symbolic math rather than, Professor Ross like pointing at, if you prefer math versus graphical, then maybe this would be make more sense to you. But this is kind of saying that each element in C, that is C sub I sub j, is the sum as k goes from 1 to n, as k walks down here, of this number, which is a sub I sub k, times this number, which is b sub k sub j. Them two numbers, let's see how to say this. This guy times this guy, and then this guy times. That's what it says. The same thing I did with the pointing. I'm not, I don't really like the math that much, but maybe this is helpful to you. Here's what it looks like in code. Okay, so I could describe this better, but I don't want to. Look, here's what it looks like in code. It's going to be a triple nested loop. You're going to walk I down these rows. That's this outer loop right here. I is walking down these rows, and J is walking across these columns, and K is doing two things. It's going down this row and then down this column. And then you're doing what's in the math. You're doing sort of what's in the math here. This, I, and then K is 1 here. So K is going from 1 to N. And then K becomes 2 here, and then K goes all the way up to N. Anyway, you're walking, you're calculating this number times this number, and then K iterates, and you calculate the next number times the next number, and then K iterates. So you're walking down the row, and you keep a running sum of these guys, and then before you come back around to the next row and the next column, you store this value in here. That's what it looks like. Matrix multiplication. Here I got a sample calculation. How about that? Here's a sample calculation right here. So we're taking this row and this column. Once again, my colors aren't working. I got to get a new printer. I got an HP printer, and it's like every couple of weeks it just stops printing in ink, and I have to reinstall the drivers. Very irritating. Anyway, look, you just multiply 1 times 5, you get 5. It's down in here. 1 times 5 and 2 times 7, so it's right here. 1 times 5 times 2 times 7 is 19. That's what goes in here. See, it's the intersection of this row and this column. This cell down here is the intersection of this row and this column. And you just keep going like that. So you would move this guy down, and you would get what's happening here. No, you would move. The next thing that would happen is you would move J down, which is this this guy here. So for this guy, do I have that? No, I don't. But for this guy, what you're doing is you're doing this row and this column. So you're doing the 1 and the 2 and the 6 and the 8. So it's 1 times 6 and 2 times 8. And that gives you 22, which goes here. The intersection of this row and this column. And here I'll do one more. So this guy here, you're doing, so now we've tried all rows. So the outer loop, right? The I iterator increments, and you're looking at this row, and then you start over with this column. So now you're looking at the 3, the 4, and the 5 and the 7. So 3 times 5 and 4 times 7 gives you 43, and that's what goes here. It's like that. And I'll let you figure out the last one. Okay, so that's matrix multiplication for a tiny little guy. Let's look at a bigger example and the whole thing. So here's an equivalence relation. We're going to do the whole thing. We're going to do, actually we're just going to do transitivity. We're just going to do matrix multiplication and use that to find transitivity. So yeah, so I've got this guy that happens to be an equivalence relation, and you can see that 3, did I draw the partition? No, I didn't, but you can see that 3 is all by himself, and 1, 2, and 4 are in a group. This is the partition that's formed on the original set A. Because remember, an equivalence relation forms a partition on the original set A. So that's this guy. It has to be R, S, and T to be a equivalence relation. It happens to be R. There's 1, 1, 2, 2, 3, 3, 4, 4. That makes it R. 1, 1, 2, 2, 3, 3, 4, 4. Happens to be symmetric, right? 1, 2, 2, 1. That's symmetric. 1, 4, 4, 1 is symmetric, right? 1, 2, 2, 1, 1, 4, 4, 1, 2, 4, 4, 2. Also happens to be transitive. For every 2 jumps, there's a shortcut. So like 1, 2, 2, 4, that's 2 jumps. There would have to be the shortcut 1, 4, and there is. And that's true for every 2 jumps, there's a shortcut, so it's transitive. All right, so it's an equivalence relation. There must be equivalence classes, and here they are. They're 1, 2, and 4, and they're 3. And I could choose representatives of the class, right? I could choose 3 to represent this part of the partition. I could choose 1 to represent this guy. Okay, this is just a review of what we've talked about in the previous video on equivalence classes. So far, that was just a review. Okay, yeah, so here's our equivalence classes, 1, 2, and 4. I've chosen 1 to be the representative of this equivalence class. I've chosen 3 to be the representative of this equivalence class. Now, typically you choose the first item in the set to be the representative, but any one would work, right? The idea with equivalence classes, this 1, 2, 4 is an equivalence class, is that they're all equivalent. So anybody could be the representative, supposedly. All right? Well, supposedly. I mean, yes. That's what I mean by supposedly. I mean, yes. All right. So we looked at some algorithms to determine reflexivity and symmetry. Those are a couple pages back, but turns out we can use matrix multiplication to determine transitivity. And why? Well, it's a little hard to explain why, but it works. So here's our relation R. That's him, right? Where is he? There he is. 1, 1, 2, 2, 3, 3, 4. It's these guys and all of these guys. Here they are in the table. And then here he is again, because we're crossing, okay, this is matrix multiplication, not Cartesian product. And we use the same symbol, but it's a different operation here. Okay, we're doing matrix multiplication here, not Cartesian product. Anyway, so we're just multiplying the matrix R times itself, right? And we're going to get this resultant matrix that looks like this. Now, this is just the matrix multiplication process that we ran through previously. And here, I think I've shown it in more detail on this next page. There's the calculations. To get this, to get this 3 right here, there's the first calculation right there. So I've got, I and J, and these are the K's. This term K is doing this one, this one, this one, this one, kind of. K not shown explicitly, but the I's and J's are shown. So you could walk through this, you could study this a little bit, and this is how you get this. Now we can look at this and determine transitivity just by looking at this answer after we've done this calculation. And basically, for every non-zero element in R2, this is R2, this is R times R. That got cut off on the notes. This is R times R, and you get R2. But for every non-zero element in R2, you must have a non-zero element in R in order to be transitive. Okay, so first you calculate the matrix product. Then you just look at each item in here, and if it's non-zero in here, then it must also be non-zero in here. That's the algorithm. Okay, that's going to be on the homework. I'm going to ask you to write matrix multiplication. I'm going to ask you to implement this matrix. Where to go? Implement this matrix multiplication thing. Generate this, and then check. Write a program that goes through here and checks these and checks. Okay. So you're going to determine. So the homework basically, for later, okay, you're going to determine reflexivity. You're going to determine symmetry. Then you're going to determine transitivity. And if it's all 3 of these is true, then this thing must be an equivalence relation. And if it's an equivalence relation, then there are equivalence classes. And I want you to, find those and find their, find the partition and find their representatives. That's what that's where we're going. So, what are we doing now? So, let's say you have an equivalence relation. You've determined that it's an equivalence relation. That is, you've checked that it's symmetry, reflexivity, and transitivity, and those are all true. And now what? Now you want to pull out the partitions. So, and this is that algorithm. This algorithm will extract the equivalence classes from an equivalence relation. Let me back up for a second. All right, so we've got this equivalence relation right here, this guy. And here he is. These are the partitions. These are the equivalence classes. And what does this thing look like in software? It looks like this. This is what we're using to do transitivity. But just look at one of these. Here, I'm going to redraw. I want to draw one of these guys over here. Even though it's here already, but look. The equivalence classes oops, there you go. Knew there was something wrong. Look, this one here, that's an equivalence class. That's this one. 1, 2, and 4. It's also, this row, because 1, 2, and 4, the rows 1, 2, and 4 all have the same information. 1, 2, and 4 have the same information. That's all you got to do is find the rows that are the same, and then 3 is another row. Okay, so you just got to find the rows that are the same, and then pull out one of those, any one of those rows, and that's the first equivalence class. Okay, and then so anyway, row 1, row 2, and row 4 are the same, so you could use row 1, and then row 3 is all by itself the same, and so you could use that for row 3. That's all we got to do. Now you could write your own algorithm to go through these guys and find who's the same. You could do that. It would be kind of a loopy-doopy kind of thing, but I got another one that I'd like you to do that I think is better. And here it is. So let me execute this thing for you, all right? So note that the first element of this original set is always going to be a representative. Here, let me redraw this one more time. Diagonals for reflexivity, and then I got that. So 1 will always be a representative, because 1's going to be a member of some class. So just make him representative all the time. So that's what I do. I mark 1 as a representative. 1 is always a representative of a class. So you could just, you could print that out straight. But I think what I had is I marked I have another array here where I've marked captains. What am I calling that? I don't, let's call it C for captains. I don't want to use R because that'll get confused with representative. So 1 is always a representative. So row 1 is the first equivalence class always. Row 1. So you just print row 1. You're printing off 1, 2, and 4. Okay. Then we just need to find, we need to find 3. So what we do here is I go through 2 to 4. So I loop from 2 to n is 4 here. Just loop through, and then just mark him as a representative, like a temporary representative. Mark him, and then look back to see if there's somebody else before him. So you'd go to row 2, you'd go to position 2, and then you just walk backwards looking to see if there's somebody else before him. Because if there is somebody else before him, he would have been chosen as the captain or a representative. That's just because that's the way the algorithm works. It's choosing the first guy. So as you go down, and you'll see. So watch. So you loop from 2 to n. You mark this guy as a representative. Then you loop from 1 back to 0, or 1 to 1, and you find that he's also in the group. So you demote this guy. You demote him to 0. Let's use a 1 to indicate these in here. So you temporarily promote this guy. Then you look back and you see that 1 was already there. So 1's already has been the captain already. So you go to 0. Then the outer loop integrates. You go to 3. You mark him temporarily as a captain. You start here. Okay. Then you look back 2 and 1, and you don't see anybody there. So 3 must be the captain. He's the first guy there. Then you continue. You go to outer loop goes to 4. So you go to 4. You go to position 4, 4, and you look back at 3. Nobody. So first you mark him. First you mark. You mark that 4 is a temporary captain. Then you look back here. Nobody. Somebody. So it's going to be 2 or maybe somebody below. And so you demote this guy. So your captains are 1 and 3. Then you just go to row 1 and print it out, and then go to row 4 row 3 and print out the whole row. That's it. Okay, we'll talk about that more later in another video, but I wanted to present it here because, well, that's what's in the notes. So we've got a couple of the things just real briefly to do. I don't want to spend a super whole lot of time on them, but this same matrix multiplication can be used to determine composition. Okay, so composition works when you have it could work on 1 set, or it could work on 2 sets, but basically if you calculate the matrix product, you're generating the composition, and that's all I'm going to say on that. And here's a calculation showing the details of the. This is good. Maybe it's another example of matrix multiplication, because I am going to ask you to implement matrix multiplication. So there's another example on it. Okay, look, one more thing. Modular or clock arithmetic. Now this has to do with, this shows up in encryption and other things. But let's define a relation as the set of all ordered pairs A, B, such that this is true, such that A mod n is equal to B mod n. That is, they have the same remainder. Two numbers A and B have the same remainder when divided by some other chosen integer n. So, for example, let's say you choose n to be 3. No, okay, R is drawn from the set of integers. So the original set A is integers. So take all integers. So A equals integers. 0, 0, 1, 2, positive integers. 0, 1, 2 all the way to infinity, right? Then generate all the ordered pairs, every possible combination of integers. And then the relation is those pairs that have the same remainder when you mod by 3. In this case, n is 3. So 0, 0. Mod 0 by 3, you get 0. Mod 0 by 3, you get 0. The remainder is 0. So they have the same remainder. These two guys also have remainder 0, right? And these guys have remainder 0. And this one has remainder 1. Let's take this one. 1 mod 3 is 1. And 7 mod 3 is 1, because 3 goes into 7 twice with 1 left over. And this guy here, 1 mod 3 is 1, and 10 mod 3 is 1, because 3 goes into 10 3 times. That's 9 with 1 left over. So the two numbers 1 and 10 have the same remainder when you mod by 3. So I've kind of grouped them here. All of these guys all have remainder 0 each when you mod each one by 3. And all of these guys of this pattern all have remainder 1 when you mod by 3. And all of these guys have remainder 2 when you mod by 3. And then there's more. There's ones that look like this, which is the inverse of, or the inverse ABBA, like 0660. All of these patterns, and then I flipped all of these and all these patterns. It's a bunch of pairs, but I'm just trying to represent the patterns that they have. Okay, it looks like this if you graph the digraphed. So you'd have 0, 0, 1, 1, 2, 2, 3, 3, because those all have the 4 and 4 have the same remainder when you mod them by something. So they're all going to be in there, and it's going to be symmetric. It's going to be transitive. So and a little bit more rigorous, a little more mathematical proof. And this is very much like a problem that's in the homework, but a little bit more mathematical proof of whether this guy is reflexive is like this. So you can use the basic definition of this thing to prove reflexivity and a little bit of math. So it's reflexive. Remember, the definition of reflexive is that every element AA in R is there for all of the elements in the original set A. So this means that using this definition of this relation, it means that you have to kind of look at the algebraic expression here and think about it that way. So like if AA is in R, then you apply this definition, just means A mod N equals A mod N, which algebraically just sort of means that AA is in R. That's kind of the weakest one to explain, but that's it. It works a little better for symmetry. So if AB is in R and BA, so symmetry means that if AB is in R, then BA must also be in R. So applying this definition up here, if AB is in R, it means that this is true. A mod N equals B mod N. And then algebraically, you can because algebra is or equivalence is commutative, right? You can move the right-hand side of the expression over to the other side of the expression. So the B mod N, you move it to the left, and then because you can do that with algebra, right? You can just flip what's on the left and the right, so then you have BA. So it means this, if this is true, which you can do algebraically, then this basically means that BA is in R, so it's symmetric. So there's that, and then you can do something similar with transitivity, because transitivity says if whenever AB and BC are both in R, then AC is also in R. So AB in R means A mod N is equal to B mod N, and BC in R means that B mod C is equal to C mod N. And then because equivalence in algebra is transitive, then you can write, if you have these two expressions, you can write A mod N equals C mod N, which basically means that AC is equal to R. So you're sort of applying the definition here and then thinking about what that means in algebra. And, all right, that's that. Before we go on, you could try this for different n's. Yeah. So if we did it for n equals 3, then it's R, S, and T, right? We just showed that it's reflexive, symmetric, and transitive by looking at these algebraic definitions. If it's symmetric, reflexive, and transitive, it must be an equivalence relation. And if it's an equivalence relation, it must have equivalence classes. And what are they? These are them. All of these numbers are equivalent in an equivalence class because they all have the same remainder 0 when you mod by 3. And all of these guys have the same, they're in the same equivalence class. And all of these guys have the same equivalence class. Okay, so by modding by 3, we've divided up the set of integers into 3 groups. We formed a partition on the set of positive integers into 3 groups, having these 3 groups. And then we could choose 0 to represent this whole group, and 1 to represent this whole, equivalence class, and 3 to represent this whole partition. Class, group, partition is kind of the same word for the same kind of stuff, right? Yeah. These are all the numbers with remainder 0. These are all the numbers with remainder 1. And these are all the numbers with remainder 2 when you mod by 3. What if you modded by 5? You'd get this, right? These would be the equivalence classes. These are all the numbers that have the same remainder 0, basically, when you mod by 5. And these are all the numbers that have this remainder 3 when you mod by 5. Okay, so this is related to very large primes. It's used in encryption. And it's related to equivalence classes, and it's all good stuff. This is why we present it right here. Okay, the very last topic is a prelude to relational database theory. All right, which we're going to do next, relational database theory. But right now, let's talk about N-ary relations, or relations with more than, well, relations with n elements in them. So far we've just been talking about, you could call it binary relations because there's 2 elements in there. There's a pair. You could call it that. You could call it binary operations. You could call it, ordered pairs, or n is 2. You can expand this concept. So you could have triplets of the form x, y, and z. Sometimes we call that triplets. Or you could have, for larger things, we use the term tuples, or n tuples. In general, we say n tuples of n is where n is some size, or this guy here is a 6 tuple. There's 6, it's a 6-element string, you know. Just to think about it another way, you could think of these as strings, right? Like we talked about at the very beginning of this stuff. It's a 6-element string. Because this stuff is, you know, all this combinatorics and counting, it's all related. Okay, here's an example. So to get a triplet or a 3 tuple, you would have to have 3 crosses. I have 3 different sets. They could all be the same set, that's possible, but to be clear, we've used 3 different sets, so we have different symbols, so it's a little bit clearer. Anyway, if you cross 3 different sets together, you're going to get this set of, you're going to get this Cartesian product, which is a set of triplets, or 3 tuples. Triplets or 3 tuples. Anyway, so the first element is in the triple is a member of the first set, and the second element's a member of the second set, and the third element's a member of the third set, and these are all the combinations you're going to get. 1 1ax, 1ay, like that, right there. 1bx, 1by, like that. Those are all the combinations. So this is just a Cartesian product that yields 3 tuples, or triplets. Now to form a relation on this, we need to draw a subset of this Cartesian product. Okay, so we can draw, relations can be drawn from this Cartesian product, and different ones, like, well, let's leave it there. Okay, that's it. Hope that was useful to you. Hope it was at least mildly entertaining. Hope you're not asleep. All right, thanks a lot. I'll see you next time. Bye-bye.